Bismillahirrahmanirrahim. Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I'm your teacher, Muhammad Ikram. Today is our lecture number 7, Applications of GAUSS Law. If you remember, last time I told you that GAUSS Law is one of the most important law which can solve very complex problem in a very easy manner. So this is what we will do it today, inshallah. So let us start with our lecture and uh, let us start with our lecture with the name of Allah Almighty. So Bismillah ar-Rahman ar-Rahim. So the first point is the location of excess charge on a conductor. Now, when we have the conductor solid, when we have the conductor is a hollow, and if there is a charge at the center of the hollow sphere or the hollow conductor, then what will be the result or the case? Next, electric field intensity due to infinite sheet of charge. Third, the electric field intensity between two oppositely charged parallel plates. And this is our topics for today. I will try to finish all the topic. If some remain, then I will switch over to the next lecture. So let us start for the location of the excess charge on a conductor when the conductor is solid. So you see in this diagram here that we have a solid conductor, right? This one, the conductor of some length L, and you see that the conductor is all solid, right? And we want to calculate, we just want that where could be a charge inside this conductor, right? We want to look at the excess charge on the conductor if there could be some excess charge. Now let us see, let us see that is from what? That is from the Gauss law, is from the Gauss law. We can write that the electric flux through any closed surface is equal E dot A equals what? That it is equal to the charge enclosed by the surface into epsilon naught. Or we can write that the charge enclosed into epsilon naught into EA. Now, if you see this conductor is that the number of, for example, look, if I connect this conductor, if this is the end A of the conductor and this is the end B of the conductor, if I connect the conductor, right, now we know the conductor contains free electrons, right? So now if I just connect, I would say that I will replace the equal number of free electron with the equal positive charge, because you know we conventionally we consider the flow of current is the flow of charge, positive charges. That is conventional. Electronically it can be through the electron. So now I want to see that where are those electrons are those positive charge, but I will use positive charge for only where those positive charge may be. I want to look those positive charges, that where those positive charges could be. So now you see that this is the entire length of the conductor, and I want to find out or to see that whether there could be charge at the interior of the conductor. I want to look for this. Now normally, you know, when I connect the conductor with uh, with, for example, with some external resistance, then there is no current flowing through it. That what does this means? That neutral, when the conductor is normally, the conductor is what? In its electrostatic equilibrium. Normally the conductor is what? The conductor is in electrostatic equilibrium. It is in what? In electrostatic. It is in electrostatic equilibrium. Normally, the conductor is what? It is in the electrostatic equilibrium. Why? Because the number of positive charges moving towards the right is the same as the number of negative charges moving towards the left. Yeah, the number of positive charge and negative charge in a conductor is the same. So we say that it is in the electrostatic equilibrium. Normally, there is no current flowing through the conductor when it is not connected to any external source. So therefore, what I will be writing that inside the conductor at the point what? At the point P, the electric field intensity at the point P is what? This electric field intensity at the point P is zero. Why? Because of this reason. Because of what? Because of this reason. So the electric field intensity is zero there. So what I can write? I can write that the charge enclosed into epsilon naught 0 into A, right? Because we already know the conductor has area, so area is not zero. So what does this means? That the charge enclosed into epsilon naught is zero, right? Now we know that the conductor, there is, that is a solid conductor and it is considered as a medium. To it has, the conductor has its own permittivity. So we already know that this epsilon naught is not zero. What does this means? That the charge enclosed is zero, that there is no charge. So if there is no, that is, what is the result? The result is that there is what? That there is no charge distribution. There is what? There is no charge distribution. Yeah, no charge lie at the interior of the conductor. Interior of what? Of the conductor. That there is what? That there is no charge lie at the interior of what? At the interior of the conductor, right? So we have one this thing. Is it clear? Now let us see that lock. Furthermore, what we can write, that what is the result then? What does this means? This means that the charges, then what? The charges then, yeah, must reside on the outer surface of the conductor. That the charges reside what? On the outer side of the conductor, as you see. So the entire charges lies where? On the outside of the conductor. So this is for what? So this is for the solid conductor. Now let us apply the Gauss law to the hollow conductor. This is hollow. And let we choose a point P, right, at the center of what? At the center of this hollow cylinder. And now we want that, will there be any, will there be any that now where the charge will reside again, even for the hollow cylinder. So now let us consider a hollow conductor is I have shown here in this diagram. Since the conductor is hollow, so there is no net charge at any point inside the conductor. Right now, let us apply the Gauss law here. That is so simple that I will do it here. What is the Gauss law? That the Gauss law tells you that it is equal to charge enclosed divided by into 1 over epsilon r times the charge enclosed by the surface. Since the conductor is hollow, so it encloses no charge. So it what? Encloses no charge. There is no charge distribution. What does this means? That this means that the charge encloses zero. So what does this means? That E is equal 0. What does this means? That E dot A is 0, or that A is not 0, right? The conductor has area, right? So it is not 0. What does this means? That E is 0, right? What this shows? This shows that there is no electric field at the interior of the hollow sphere. So still this signifies that if there could be any charge on the conductor, the charge will lie on the outer surface of the conductor, as in the previous case we have found that it came to be here. It does not reside on the interior, only on what? Only on the exterior. So here the excess charge will again, if any, they will what? They will lie on what? On the outer surface, right? So charges always tends to lie on the outer surface of the conductor only. Two cases. Now let us see another case. And in this case, if we have what? Again, that we wish to find out the that is, we now wish to find out what? To find out the charges here, all around here at this interior surface. Still it is sorry, still it is a hollow conductor, right? And now this time I place a positive charge at the center of this hollow sphere, as you see. It encloses what? It encloses a positive charge Q that it encloses. And now I just want to see that where the net charge will lie. So in this case, as you see, we have placed charge Q inside the hollow conductor. Now we insulate it so no charge can jump from the surface to another. Now if we use Gauss law with a Gaussian surface S, this is the Gaussian surface, as you see the Gaussian surface S, then the net charge of what it enclosed has to be 0, because there was no charge transfer between the charge and the conductor, right? So what does this mean? Let us see, for example, if there is a positive charge, so because of the electrostatic induction, so if I just make a front view of this, as you see, this is the front view, right? As you see, look, the front view of this conductor, as you see, which encloses what? Which encloses a positive charge, right? Like this one. Then what happened? Because of this electrostatic induction, there will be what? There will be an electrostatic induction, and this electrostatic induction will cause all the negative charge to just to accumulate here, right? And when the negative charge tends to move this way, the positive charge will be tending to move atop, right? And again, you see that there is no charge inside what? Inside the conductor in the metallic part. What does this means? This means that if you let me do it with a narrow pen like this one, as you see, look at this portion, no, still no charge, no charge even at this interior point. So the excess charges always lie at the outer surface. The excess charges always lies what? At the outer surface of the conductor. There is no charge distribution inside the conductor. So this is the first case. We have the second case is what? All the three cases I discussed. The conductor is solid, when the conductor is hollow, and when there is a charge at the center of the hollow sphere. Now let us see the electric field intensity due to infinite sheet of charge. Electric field intensity due to, that is electric field intensity due to infinite sheet of charge. Due to infinite sheet of charge. Number two, electric field intensity. Electric field intensity due to infinite sheet of charge. Now, again, we will be using the Gauss law, right? By using what? By using Gauss law. By using Gauss law. See here. First of all, look, if we have this, the infinite sheet of charge as you see, and I want to calculate the electric field intensity at this point P, that what is the electric field intensity at this point P? Let me erase this. I want to calculate what? I want to calculate the electric field intensity at this point P. That what will be the electric field intensity at the point P as you see, because of this infinite sheet of, because of the infinite sheet of charge. As you see, this one, there is charge distribution. Now the question is, why infinite sheet of charge? Infinite sheet of charge because that, so that we should have uniform electric field, right? If the sheet is not infinite, then there is greater, always there is greater concentration of the charge at the sharp edges. The sharp edges tend to occupy more charges, or the charges always tends to move towards the sharp edges. This is why we use infinite sheet of charge, right, for simplicity. So you see that, look, we want to calculate what? We want to calculate the electric field intensity at these points, right? The electric field intensity at the point B. Now, then what is the first point? The construction. In order to apply the Gauss law, what is the Gauss law? Gauss law tells us that the electric flux through a closed surface is equal to the charge enclosed by that surface into epsilon r. Now, in order to apply the charge, the Gauss law, sorry, we first need the enclosed surface. So let us see, look at the point P. First, we need to construct the construction of the Gaussian surface. Construction of what? Of Gaussian surface, the closed surface we need to construct. So you see that it is in the form of what? It is in the form of this cylindrical shape, right? As you see, look around the point P, where we wish to calculate what? To calculate the electric field intensity. Now you see we have three surfaces as you see in this diagram. Look, this 3D diagram here, the cylindrical Gaussian surface. And in this 3D diagram, you see, look, we have one, this what? This is called the curved surface. Curved surface. So we have one, the curved surface. That surface I label it as the curved surface. I label it as S1. This curved surface, I label it as what? S. Yeah, let's say first of all we have one, this cross-sectional surfaces. One, this surface as you see, like this one here as you see, and one, that one. So how many surfaces do I have? One surface I have, let I call it the surface, this surface is surface S1. This surface I would call as the surface S2, and one, the surface S3. This is the curved surface. Curved surface. So due to this infinite sheet of charge, that is, there might be flux due to the three surfaces. So when I apply the Gauss law, so electric flux due to surface S1 plus electric flux due to the surface S2 plus electric flux due to the surface S3 into the charge enclosed by epsilon naught. Now, what is this charge enclosed? For the charge enclosed, I define a term, surface charge density. Surface charge density. And what is that surface charge density? This surface charge density, I just show this by a sigma, which means charge enclosed per unit area. So this surface charge density means the charge enclosed into A, this one. So what I'll be writing here, sigma A in this case. Now let us see what will be the flux through the surface S1. Since if you just see, look for the surface S1, for the surface S1, if you see here, you have look this surface S1, and you see that the area vector A and the electric field intensity, they both are in the same direction. So theta is what? 0 degree. And you know what is the electric flux? E dot A. So definitely this electric flux will be EA maximum. A is the area here and A is the area here. So what I'll be writing here for the flux, it will be EA. And for this, similarly, the same situation, the area vector and the electric field intensity are along the same direction. So for the surfaces to EA. Why? Because A1, if I just label this as A1 and this is A2. So you see A1 equals A2 is equal to A. And what will be the electric flux through the surface, through the curved surface? And the electric flux through the curved surface is what? It is 0 into sigma A into epsilon naught. Now, why it is 0? The answer is very simple. Because of the fact that if you just see, look in this case, the curved surface, the normal is in this direction. For example, if this is area, and you see the electric field intensity, it is in this direction. So what is theta? Theta is 90 degree. And you know already that the electric flux is what? It is this electric flux is EA cos theta. So you see EA into cos of 90 degree, which is 0. So the flux through what? Through the curved surface of the cylinder is 0. So what does this means? This means that 2EA is equals sigma A epsilon naught, which means that E equals sigma by 2 epsilon naught. What is the result? The result is that the electric flux due to infinite sheet of charge depends on the surface charge density and the medium, right? It does not depend on the shape or on the area, right? It only depends on the surface charge density. Remember, in one interesting, the most promising result, interesting result, that it does not contain R, right? It does not contain what? R. That whether the point P is nearer or away, it doesn't make any difference, right? The electric field intensity will be the same for infinite sheet of charge. So that is very important point, that it does not contain any R. So it means that whether if you are closer to the infinite sheet or a bit away, make no difference. Electric field intensity is the same uniform for infinite sheet of charge everywhere, right? So that is the next case. The third case is that of the for oppositely charged parallel plates. Third, for the oppositely charged parallel plates method. Two methods I will solve. The first method, that is usually from your book. Second, that is a common sense method, and that is using application with an application, and that I will tell you from my side, right? So let us see the two oppositely charged parallel plates. Here you see, for example, look, when we have this, right, as you see, that is the interior like this one, and one you see like this one, as you see. And then there will be what? This is plate A, and this is plate B, or 1 or 2. So what does this will show applying the Gaussian law. What is the Gauss law? The Gauss law tells you that the electric flux through any closed surface is equal the charge enclosed by epsilon naught, the medium between them. So what we have actually done, we have constructed here what? A Gaussian surface. We need to construct the Gaussian surface, and we want to calculate the electric field intensity at the point P anywhere, right? That what will be the electric field intensity due to this. So you see that the upper plate is positive and the downward plate is what? Negative, right? And now let me construct the Gaussian surface first. And I would like to construct the Gaussian surface by using this green pen. You see, look, I just construct this by using a 3D shape or a 3D diagram like this one. As you see, look, you have seen a 3D diagram. Half is inside it. The plate A, this is plate B. Now you see that how many surfaces you have. You have one the down this surface, one you have the top surface, one you have this surface, and one you have this surface. So surfaces 1, surfaces 2, surfaces 3, and surface S4. Let us see that what could be the electric flux through this one. Now, as you see, look, if you apply, then you have the electric flux due to surface S1, electric flux S2, electric flux S3, electric flux S4, and you have the charge enclosed by the surface, and you have one this thing. So this is so easy. Look at this thing here. From all the surfaces, S1 except the flux is 0. Why? Because that surface of the cube, which I have like this surface, it is what? The surface is what? Surface is inside the conductor. Inside the conductor. And you know, there is what? And there is no charge distribution at the interior. No charge distribution at the center or interior of the conductor. It encloses no charge. This is what the first case we have done, right? Now the surface S2 and S3, this also contributes zero flux, and this also contributes zero flux. Why? Because theta is 90 degree, right? Look, the electric field intensity is downward. As you see, the electric field intensity is in this direction, E, and you know that the surfaces S1 and S3, they make angle of 90 degrees, so flux will be zero. So the only surface which left is the only surface that left is the surface S4. Electric flux due to the surface S4, 5 S4, that contributes, right? And that contribution is E, electric flux, and the area of the bottom surface, EA. And the charge enclosed, you already know, sigma A epsilon naught. So what does this means? This means that the electric field intensity between the oppositely charged plate anywhere is sigma epsilon naught. There it was. Sorry, I'm so sorry. Here is half. There is half 1 or 2 epsilon naught. There I wrote. There I forgot. So you see that, look, what does this result mean? That epsilon naught into what? It is this one. What does this means? That electric field E is uniform. E is uniform everywhere. Inside what? Inside the two plates, oppositely charged plates, right? And this is why we always draw these lines equally spaced lines. And if you remember introducing you electric field lines, I told you when the electric field lines are equally spaced or parallel, then the electric field is uniform there. So one is this result. This is the most important result. Second, it does not depends on R. It depends on the surface charge density. Why it does not depends on R? Because it is the same. For example, if I choose any 2 points, the point A or the point B, electric field intensity will be the same. EA, EB. So EA is the same as EB, as E, right? So this thing. The second method, as I told you, I'll be telling to you second method. And I told you about this, that this is application with an application. Application within what? Within applications. And this is so easy. Electric flux, EA, the net electric flux. You know, and that how the electric, that is the net electric flux, yeah, the electric field intensity, is we know that for the positively charged plate, electric field intensity is what? It is the sigma by epsilon naught. And for the negatively charged plate, it will be sigma into epsilon naught, right? That is the same because whether the plate is like this, so whether it is positively charged or whether it is negatively charged, it is the same plate, whether it is negatively charged or positively charged. Oh, sorry, negatively charged or positively charged. Density is what? Surface charge density is the same. But you know that the electric field, you might be saying that that is for both, in both the case the electric field intensity is in the same direction from A to B for the positive and negative. So what will be the total electric field intensity? Because of the E plus into the E minus. This is using application within application. I use Gauss law within Gauss for this case, the first application I'm using in the third. So what will happen? It will be that is sorry, 2. So you see sigma 2e epsilon r plus sigma 2 epsilon r. What does this means? It means that sigma by epsilon r, right? So this is an easy solution, but I think it is not common. I did not see somewhere in the books. Maybe it might be in some books, I don't know, but I did not see it. So these are the application of the Gauss law. So thank you very much the for the today lecture, and inshallah in the next lecture we will talk about electric potential. Thank you very much, and Allah Hafiz.